Hey folks, Astrolin here. So I kind of wanted to talk about something really cool that's been developing over the past year and a half with citizen science. So as you guys know, I recently kickstarted LCO with Project Eyes in the Skies, and the initial use was for allowing people to have access to astronomy equipment in general that do not have access. And the goal for this particular project that I have developed was to utilize the detect code, which was submitted by a user on Exoplanet Watch called the Detailed Exoplanet Transit in Exoplanet Characterization tool. The purpose of this tool was to study potential exoplanet candidates, stellar variability, stellar pulsations, and as well as using synthetic mass estimations, which estimates mass via relationships with the radius calculations. Initially, the goals were for citizen science usage, meaning the code is free. The code is free of access to all users who want to study and get familiarized with the exoplanet codes on GitHub and Collab. So it will be on both if you do have the packages that are necessary to be installed. The code will allow users to basically schedule follow-ups on ground-based telescopes and accurate ephemeris calculations based off mid-transit, orbital period, and transit depth calculations. This actually has synthetic mass derived from the work of Chen JJ2, and actually this is the work that he's usually done. It is the forecaster plugin, I guess, for Python, and I was continuing on the work of this because there were some problems with this code that I could not figure out why it wasn't working, and for some odd reason, I think it was because some Python packages weren't allowed, or they were just having confliction with other packages. So I made my own synthetic mass relationship, and actually it is decently accurate based off of what I know about exoplanetary mass and exoplanetary radii in general. What I wanted this particular code to do is allow people to have access to be able to do exoplanet observations with TESS data and to gather TESS light curves, and actually it's to detect an exoplanet faster using transit least squares algorithm and the periodogram from a custom Lomsgargle periodogram, which was actually trained by ChatGPT, which is really cool. Actually, this entire code was made by AI, and it's impressive that AI was able to do everything and merge the code snippets that I was needing to merge to basically get this thing up and running. And actually, this is like the basic layout. The packages you will need specifically are NumPy, light curve, transit least squares, warnings, Seaborn, SciPy, Bokeh, Matplotlib, and AstroQuery. The reason why you need these is because this code actually has its own custom filter, and it allows to do certain things that I don't think any other code does, and that I've seen at least. Now, this is actually a little bit tricky because in terms of actually applying specific requirements for known planets and stuff like that. Actually, we're going to take a known case study, and we're going to go with WASP. I think it was 129b, and actually I got this right here, so we can go here, click the tick ID information here, and we can put the tick ID here, and then we can go on the copy paste notebook that I already have and get the sector informations that are there from this particular line. I'll actually link this in the description down below. So we got sector 10. We're going to analyze sector 10. And the cool thing about this is that you can actually, if you see another higher confident SNR period detection, you can actually adjust the period to try and see if the code can actually find that planet. And so if that is confirmed, then you might have two planets inside the system, and I think that's really cool that this code might actually potentially be applicable for that. So this part's a little bit tricky because I haven't found a way to incorporate automatic star radius and star mass, because I've noticed that some codes or some exophot targets don't have star radius and star mass at all. So that was kind of concerning to me, because in order for us to estimate the accurate radius of the exoplanet or the type of object, it would be needed to be derived from the host star radius itself, and as well as the mass. So that was the tricky part that I had to go through when I was trying to train the code to do that. So the star radius could be derived from exofop, and the tick information here, and as well as the stellar parameters down here, you would get the radius from here. So you would copy the radius with Control and C, and then you would put the radius in here, and then the star mass would be about a 1.1. So once that is done, you're pretty much all set to go. So we're going to go ahead, click right Control Enter, and it should start up the code. So as you can see, it already detected a period, 5.75 in the highest SNR possible, and the radius is 107,430 kilometers, which is actually pretty accurate for the radius of WASP 129. And the orbital period that it detected the most in the TLS periodogram is 5.75 days. And I think that's really cool. And it allows you to plot the transits where they occur too in this fourth transit, fourth plot chart, my bad. It also allows you to have a phase folded curve of all the transits detected. So you could get a really nice looking light curve if you want to publish a paper on it. And I think that's really cool. And the in-transit versus out-transits are still, like I said, in the works, but it looks like this might, yeah, it's really cool. So the synthetic planet mass is still kind of being assumed, I guess. I'm not really entirely sure if that's accurate. I guess it had an estimated mass of like 314 something Earth masses from last I've known, so I can actually look this up. So WASP 129b mass, so I can actually look this up. So its mass is 1 Jupiter mass, so I can actually look WASP 120, okay, so 1 Jupiter mass, in Earth mass, so that's roughly about 318 masses. So this code is a little bit off with the synthetic planet mass, which we're still training to do, but it is really good for detecting Neptunian-sized objects and all that stuff as well, so that's still being reworked and stuff like that, so. And here's a target pixel file showcasing the star as well as another star here. And so to give you an example of a decent fit in synthetic mass, I am actually taking a known candidate that I have been studying for a while and actually came out to be pretty accurate. I was really impressed for the estimated mass estimates. So here is a really good application for this particular code. So transit depth, 9.93 parts per thousand. That's still off. I completely forgot to switch my star radius. So 0.406, and star mass is 0.405. I completely forgot to do that. That was so far off. And there we go. Planetary radius is 28,170 kilometers, which is what you would expect in a sub-Neptunian-sized object. So, what does this mean? Well, it means we detected a sub-Neptunian-sized object that we can actually use to follow up. So, what's really cool is that if you do end up getting access to like radial velocity equipment, or if there's a paper that's somewhat being published that is doing radial velocity, you could check against the synthetic mass of the planet and actually check against the actual mass of the determined planet based off the radial velocity and get a second opinion, basically. And the phase fold for this is really interesting, in my opinion, because we got more periods that seem to be showing up here. So it's not just this planet that is highest in SNR. So we also had a period for 7.79 days, which we actually have found to be true. So I'm kind of curious if we take that period and estimate it. So we'll go period min 7.7, and we'll do period max of 8. And we'll see what pops up. Okay, so that might have worked. Okay, so it did detect the period. Oh, wow. That's cool. Synthetic planet mass 31 Earth masses. That's interesting. So that might explain the gravitational influence on the other planet. Wow. Okay, so we might have just proved something for this particular investigation. Oh yeah, that's gotta be significant dilution if it's on the same curve as the first planet. Okay, so if it's on the first planet, yeah, that explains why the depth is a little bit bigger. Wow. Okay, so that's that's indicative of dilution. I hope you guys enjoyed this video. If you did, feel free to support the project by getting the project yourself on GitHub, and as well as potentially subscribing to the channel, as I will be coming out with frequent updates on this code itself. If you want to try to participate in this type of work, feel free to DM me. I am on Slack on Exoplanet Watch, and so shout out to Exoplanet Watch and all those guys. You guys are amazing. And as well as the Global Sky Partner Initiative for LCO. LCO does amazing stuff with award-winning projects and stuff like that, and I'm giving those guys a shout out too. Basically, we're gonna try getting more people involved, searching for exoplanets, and as well as possibly just classifying exoplanets in general and teaching them about them. And so that's basically what the whole goal is for this whole thing. And yeah, so until next time, I will see you guys around.